At the center of the Milky Way sits an object 4 million times the mass of our Sun, so powerful it bends light and sends nearby stars whipping around like race cars on a tiny track. This is Sagittarius A*, a black hole in the simplest terms, a place where gravity wins so hard that not even light can get away. Imagine a cosmic drain, but without the clog of lost socks. You'll watch how clever people used ordinary tools, telescopes, patient observations, and a lot of math-free detective work, to reveal something we couldn't see directly, by watching how stars danced around an invisible partner. By the end of this video you'll understand why this invisible heavyweight matters to the story of our galaxy, see the surprising ways we captured its image, and get real-world comparisons that make the physics feel more like neighborhood gossip than sci-fi. Stick around and you'll leave being able to explain Sagittarius A* at a dinner party, impress your friends, and maybe even make a few jokes about space drains, all without complex terms or a PhD. The heart of our galaxy. Astronomers point to a compact, extremely heavy object sitting at the very center of the Milky Way that has a mass roughly 4 million times that of our Sun and lies about 26,0 light-years away from us. It cannot be seen with ordinary telescopes because thick clouds of dust block visible light, so scientists use radio, infrared and 10th-ray telescopes to study its behavior instead. The object shows up as a bright point in radio maps and as occasional flares in higher-energy light, which tells observers that something energetic is happening in a very small region. You can think of those telescopes as special sunglasses that let us peer through the galactic haze. The object behaves like a black hole, which simply means a place where gravity is so strong that, past a certain boundary, nothing can escape, not even light. That boundary is called the event horizon, and it acts like a point of no return. Crossing it is like stepping onto a one-way merry-go-round you can't leave. Gas and dust that come near do not fall straight in cleanly, they spiral, heat up, and glow before disappearing. Picture water swirling down a drain and glowing because the pipes are on fire, not exactly, but close enough to give a feel for the drama. Around this central mass, stars race on tight orbits, some reaching speeds of a few thousand kilometers per second during the closest parts of their paths. Those stars act like test particles, tracing the gravity of the invisible object and proving its presence. One can liken their motion to cars zipping around a roundabout. If you watch carefully, the pattern of their movement shows you where the roundabout center of mass sits, even if the center itself is a dark pole. These stellar orbits are one of the clearest, everyday-style pieces of evidence that something extremely massive and compact hides there. Despite all that mass, its direct effect on our neighborhood is negligible. The Sun and the planets are so far out that the central object's gravity is no more important for Earth than a heavyweight sitting at the center of a distant carousel. You feel the motion nearby, but you won't be pulled off your horse. Occasionally the center emits bursts of 10th rays and infrared light when clumps of gas get close and heat up, like a sleepy dragon clearing its throat. Most of the time, however, it is relatively quiet compared with the screamingly active centers seen in some other galaxies. Observing this object is a challenge that mixes clever techniques and a bit of patience. Long radio arrays combine signals to act like a giant telescope, and infrared instruments peer through dust to follow stars dancing in tight orbits. Scientists compare the observations to predictions from physics and find a good match, which strengthens the black hole interpretation. Put simply, it's as if you can't see a person behind a curtain but you can see the curtain rippling and the furniture moving in a way that only a very particular kind of guest could cause. What is Sagittarius A*? At the center of our galaxy sits an object so dense that its gravity wins every tug-of-war, even with light. Scientists call it a supermassive black hole, which simply means a place where an enormous amount of matter has been squeezed into a very small space and the gravity is so strong that nothing passing too close can escape. Think of it like a cosmic trapdoor. Once you step past the invisible edge, you're not coming back. The edge has a name, the event horizon, but you can think of it as the point of no return, like rolling off a cliff where your parachute forgot to show up. This particular central object is known to astronomers as Sagittarius A star. It contains a mass roughly 4 million times that of our Sun, yet that mass is concentrated into a region that is very compact on galactic scales. Picture cramming millions of heavy bowling balls into a room the size of a small neighborhood. The crowding gives you a sense of how extreme the situation is. Despite the dramatic description, the environment around it can be surprisingly calm most of the time, not the non-stop fireworks you might expect. Researchers study this object by watching how stars orbit around it and by catching bursts of light from hot gas falling inward. Observing those stars is a bit like timing cars on a roundabout to infer the size of the central island you can't see. Occasionally gas gets heated to very high temperatures and lights up in infrared or 10th rays, producing flares that signal something passing close to the edge. Telescopes tuned to radio waves also pick up a steady, compact source of emission from that region, which helped point scientists to its presence in the first place. It matters because this object anchors the Milky Way and shapes the motions of stars in the central region. By studying it we learn how gravity behaves in extreme conditions and get clues about how big galaxies organize themselves. For everyday perspective, think of it as the hub of a busy wheel. You don't see the hub from far away, but everything on the spokes is influenced by it. And yes, for all its power it still manages to be rather introverted most of the time, a huge, quiet heavyweight at the galaxy's center, occasionally burping out a flare like a sleepy dragon. The early radio whisper, first clues. The center of our galaxy revealed itself not by bright starlight but by a faint radio signal that stood out like a whispered secret in a crowded room. Radio waves are a form of light we cannot see, and they travel through the thick clouds of dust that block ordinary telescopes. In everyday terms, it is like hearing a distant radio through a wall. You cannot see the person playing music, but the sound tells you something is happening on the other side. Simple and useful. Astronomers gave that tiny beacon a name, and careful observations showed it was unusually compact yet surprisingly energetic. Compact means the source comes from a very small region in the sky, not spread out over a wide area. Think of it as one bright lamp rather than a whole string of fairy lights. The pair of researchers who pointed this out made a clear claim: here was a concentrated radio source sitting right at the Milky Way center. It was small, it was bright in radio waves, and that mix was strange enough to get everyone's attention. Funny how the universe can be dramatic without even trying. Because optical light was blocked by dust, radio served as the sleuth's magnifying glass. Radio telescopes combined signals from several dishes to sharpen their view, much like how several ears listening together can pinpoint where a sound comes from in a noisy room. The early radio measurements showed a point-like source rather than a glow, and that pointed to something energetic packed into a tight space. Everyday analogies help. A tiny speaker blasting loudly will draw attention more than a whole band playing softly across the street. Those first radio clues did not give a full explanation, but they narrowed the possibilities. Either there were many ordinary sources piled so tightly that they seemed like one, or there was a single, extreme engine powering the emission. The compactness and brightness leaned toward the latter idea. Astronomers started treating the region like a locked box and the radio signal as a key. It told them that the center was hiding something powerful and unusual, and that further sleuthing with other tools would be needed to understand what that power really was. Humorously enough, the galaxy's center behaved like a shy celebrity, almost invisible in regular light, but impossible to ignore when it whispered into the radio microphone. From name to notoriety, how it got its star. Sagittarius A * sits at the heart of our galaxy, and its name tells a compact story that is easier to unpack than the object itself. Sagittarius points to the patch of sky in the constellation of the same name, a way astronomers mark directions much like using a neighborhood on a map. The A labels one of several bright radio blobs in that crowded area, so think of it as House A among many on the same street. The little star symbol tacked on the end is more than decoration. It marks this particular blob as unusual and attention-grabbing. The star symbol was chosen as a quick, memorable flag. Scientists often use short labels to keep conversation and papers tidy, and the asterisk works like a gold sticker on a project. It signals, this one is special. In everyday terms, it's like circling a favorite cafe on a city map and adding a smiley face. The pronunciation A* made the tag even stickier, easier to say than a long catalog number, and with a built-in hint of celebrity status. People like short, catchy names. It helps headlines and classroom explanations catch on. What pushed Sagittarius A* from a tidy label to something famous was what telescopes revealed about its surroundings. Observations in radio, infrared, and 10th-ray light showed stars swooping around a point so small yet exerting so much pull that only an incredibly dense object could explain it. To picture that, imagine a tiny marble controlling the motion of bowling balls around it. The size comparison is shocking. Those tight, fast orbits are the strongest practical clue that a supermassive black hole, a place where gravity is overwhelmingly powerful, sits there, not visible like a star, but unmistakable by its effects on nearby stars and gas. The name itself helped the idea spread beyond specialist journals. Teachers, journalists, and the public could say A* and immediately refer to the mysterious engine at the galaxy's core without wading through technical labels. The simplicity is practical. Short names travel better in conversations and social media, and the star symbol carries an intuitive meaning of importance. Scientists still use the more formal catalog names in detailed work, but for storytelling and outreach, Sagittarius A* wins every time. Catchy, evocative, and just a little bit cheeky, which fits a cosmic heavyweight with style. Seeing the invisible, overcoming galactic dust. Galactic dust sits between us and the center of the Milky Way, and it soaks up and scatters ordinary visible light, which is why the heart of our galaxy looks dark in optical images. This dust is made of tiny solid grains, roughly the size of smoke particles, that block blue light more than red light and make distant objects appear reddened, similar to how the sun looks redder at sunset because sunlight passes through more atmosphere. In everyday life you see the same effect when headlights get fuzzier in fog. The light is scattered and the details vanish. So when astronomers point normal telescopes toward the center, they are often looking through a thick, dusty veil. Longer wavelengths of light cut through that veil much better. Infrared light, radio waves, and sub-millimeter waves are less affected by the tiny dust grains, so instruments that work at those wavelengths can probe the hidden core. Think of it like sound. Low bass notes travel through walls better than high notes, and in astronomy long wavelengths play the role of the bass. Observatories such as the Keck and the Very Large Telescope use adaptive optics to sharpen infrared views by correcting the blurring effect of Earth's atmosphere, while space telescopes that detect infrared light avoid the atmosphere altogether and give clear views too. Combining many telescopes together is another trick to see small details at the center. This technique is called interferometry, which means using many small eyes to act like one huge eye. The Event Horizon Telescope, for example, links radio dishes around the globe so they behave like a single telescope the size of Earth, allowing astronomers to resolve the tiny silhouette of the black hole surroundings. It's like arranging lots of small binoculars so that together they can pick out a postage stamp pattern on a distant wall. To make that work, all the telescopes record data in perfect sync using extremely precise clocks, and then scientists stitch the signals together, a careful process that demands both math and patience. Other tricks help too. Measuring how the orientation of light changes, called polarization, reveals magnetic fields near the center, and watching bright flares in 10th rays or infrared shows when matter gets heated as it falls toward the black hole. Those different kinds of light act like different diagnostic tools. One tells you about heat, another about motion, another about magnetic structure. Observers must also fight the messy real world, variable weather, noisy signals, and the fact that the galactic center itself flickers and changes, so they take many measurements, combine them, and compare results from different wavelengths to build a consistent picture. With all these methods working together, the once hidden nucleus of our galaxy becomes accessible, like switching from cloudy sunglasses to a pair that lets you finally read the tiny print. The rising power of infrared astronomy. Dust in the plane of our galaxy blocks visible light, yet infrared light threads through that dusty veil and lets astronomers see the crowded neighborhood around the galaxy's central black hole. This is not just a prettier picture. Infrared reveals stars that would otherwise be invisible, including the close-in, fast-moving stars known as S-stars that swing around the black hole. Those stars act like tracer particles in a fluid, showing how strong gravity is in that region. In plain terms, infrared is the right kind of light for peeking where ordinary light cannot go. Earth's restless atmosphere smears starlight into a blur, but clever tricks can put the image back into focus. Adaptive optics use deformable mirrors that change shape many times per second to cancel out the twinkling, rather like tiny, frantic optometrists nudging a lens until the view clears. Observatories with big telescopes on mountains use these techniques to study the infrared glow near the center, and instruments that combine light from several telescopes, working together like a team of people squinting to read a tiny sign, can reach even finer detail. Laser guide stars provide an artificial reference point in the sky, and no, the telescopes are not trying to start a disco, they're just finding a steady spot to compare against. Infrared also captures bursts and flares of energy from hot gas as it brushes past the black hole, moments that tell a story about how matter behaves under extreme conditions. When that gas heats up, it shines in infrared wavelengths, and scientists read those signals much like a detective reads fingerprints. Spectroscopy is simply separating light into its ingredients so you can tell what's in the mix. Space telescopes that work in infrared avoid the atmosphere entirely and can pick up fainter heat signatures, similar to how a night vision camera sees what your eyes can't. Your TV remote is an everyday example of infrared made useful, and the same kind of light helps us study the heart of the Milky Way. The practical payoff is real and ongoing. By tracking the infrared positions and motions of stars near the center, researchers measure how massive the central object must be and test our ideas about gravity. That continuous watching requires stable, sensitive infrared instruments and long-term patience, much like tending a garden to understand how plants grow. Future improvements in infrared sensitivity and sharper imaging will reveal even tinier details of that chaotic region, and if telescopes could wear sunglasses, these ones would be the coolest. 10th rays and outbursts, flashes from the darkness. 10th ray telescopes in space catch sudden, bright flashes coming from the region around the galaxy's central black hole. These flashes are bursts of very energetic light that our eyes cannot see. Think of 10th rays as the cosmic equivalent of a camera flash that only special detectors can spot. Observatories such as Chandra, XMM Newton, and New Star have recorded these surprises, and they arrive unpredictably, sometimes several times a day and sometimes with long quiet gaps. Short bursts can last for a few minutes, while stronger outbursts can glow for an hour or more, so the action is fast on cosmic terms. The bursts vary in strength, sometimes making the black hole's neighborhood shine dozens or even up to a few hundred times brighter in 10th rays than its usual, sleepy state. This rapid change in brightness means the source of the flash must be small. Light cannot reorganize itself instantly across a huge space. In plain terms, if the light in a stadium suddenly dims and brightens in a second, the change must come from a tiny spotlight, not from the whole crowd turning on their phones. That same logic lets astronomers say the flares come from a region close to the black hole's edge. What causes the fireworks? One leading idea involves magnetic field lines tangled near the black hole that suddenly snap and reconnect, a bit like the sudden pop when a twisted rubber band finally breaks free. That snap releases a lot of energy and slams particles to high speeds, and those fast particles then produce 10th rays. Another possibility is that a small clump of gas, or even a discarded chunk of something like a comet or asteroid, gets too close and falls in. As it spirals, friction and compression heat the matter until it glows in very energetic light. Both ideas are plausible, both have simple analogies. Magnetic reconnection is like a short, sharp lightning bolt above a thunderstorm, while an infalling clump is more like tossing a rock into a campfire and watching a flare of sparks. Sometimes the 10th ray flares line up with brightening at infrared wavelengths, and sometimes they don't, which gives important clues. When both types of light brighten together, it suggests the same population of speeding particles is doing two jobs. One process makes infrared light and a related process boosts that light up into 10th rays. When only 10th rays flare, a different mechanism might be at work, such as energetic electrons scattering lower energy photons to higher energy. That scattering process can be thought of like a tennis ball, a low energy photon, getting whacked by a racket, a fast electron, and flying off much faster. These flashes are more than fireworks for astronomers, they are diagnostic tools. Because the flares are brief and come from a small region, they constrain how matter behaves in extreme gravity and how magnetic fields behave near the hole. Observing when and how the brightness changes gives hints about the speed of particles, the strength of the magnetic fields, and the temperature of the gas. Coordinated campaigns using multiple telescopes at different wavelengths act like putting together pieces of a puzzle. An 10th ray flare plus an infrared flare plus radio monitoring can reveal whether the energy came from particle acceleration, a tidal snack on a small object, or some other mischief. In everyday terms, tracking these outbursts is a bit like watching a stormy seashore through blindfolded windows using different types of sensors, a microphone for thunder, a pressure gauge for gusts, and a thermometer for warmth. Each sensor adds context that turns noise into a story. And while astronomers have strong ideas and good evidence, there are still surprises, occasional flares that don't fit neatly into the main models, so the black hole keeps a sense of humor and mystery. New observations and better coordination between telescopes continue to sharpen the picture, one flicker at a time. The stellar ballet, stars orbiting the invisible giant. Astronomers can actually watch individual stars racing around the very center of our galaxy, and those motions are like fingerprints that point to a single, incredibly heavy object. The mass inferred from those orbits is about 4 million times that of our Sun, concentrated into a space so small that the only sensible explanation is a supercompact object. One especially famous star completes a full loop in roughly 16 years and swoops in close, to within a distance comparable to a few hundred times the distance between the Earth and the Sun, reaching speeds of several thousand kilometers per second at closest approach. That combination of high speed and tight orbit is what tells scientists the central object is both extremely massive and extremely compact. Watching the stars move is how researchers measure the invisible. If you whirl a stone on a string faster, the string has to pull harder to keep it in a circle. The same idea works in space. By tracing the path of each star and timing how long it takes to go around, astronomers calculate how strong the central pull must be. Observers use infrared cameras to peer through the thick dust that blocks visible light, and they correct for Earth's wobble and blurring in clever ways so the stars don't look like smeared paint. Think of it as using night vision goggles and image stabilization to film a hummingbird in a thunderstorm. Those stellar paths do more than just weigh the invisible object, they also test how gravity behaves when it gets intense. Light from a star slows down a bit and stretches to redder colors when it climbs out of a deep gravity well, so precise color measurements reveal that effect. Orbits themselves show tiny quirks. Instead of repeating the exact same ellipse forever, the closest point nudges forward a little each time, like a runner on a slightly banked track who drifts outward with each lap. Detecting these small deviations is a way to check Einstein's ideas about gravity under extreme conditions, and the results so far match what the theory predicts. The crowd of fast-moving stars near the center includes some surprisingly spry, relatively young stars, which raises a puzzle. How did such stars get so close to the compact powerhouse without being torn apart? Some may have been pushed inward by interactions with other stars or gas, while others could be the result of dynamic reshuffling after cluster encounters. Picture a busy nightclub where a handful of dancers end up right next to the bouncer by accident, but on a scale that makes the bouncer about 4 million times heavier than the Sun. Ongoing monitoring keeps revealing new members of this stellar troupe and yields occasional stellar surprises, and that steady attention is how astronomers keep learning about both the dancers and the stage they orbit. Weighing the beast, measuring the mass. Astronomers figure out how massive the object at the galaxy's heart is by watching the stars that race around it. They measure how long a star takes to complete its lap and how big that lap is, and then plug those two pieces of information into the rules of gravity to get the mass that must be pulling on the stars. It's the same basic idea as timing how fast a child spins on a merry-go-round to guess how heavy the center pole must be. The faster and tighter the circle, the heavier the center needs to be. In the case of the compact radio source known as Sagittarius A*, those stellar motions point to a central mass of about 4 million times the mass of the Sun. Infrared telescopes are key because dust blocks visible light in the galactic center, so astronomers watch in wavelengths that pass through the dust. Using repeated images, they trace individual stars as they swing through long, looping orbits. Some of these orbits are very elongated, taking a star close to the center and then far away again, and each close pass gives a strong clue about how much gravity is packed into the center. Think of it like watching cars on a roundabout. Watching a car speed up on the inside lane tells you there's a much stronger pull toward the middle than if cars coast slowly. Radio instruments add another piece of the puzzle by limiting how big the glowing central source can be. If the light comes from a region that's as small as the radio maps show, then packing millions of solar masses into that tiny space gives an extremely high density. No normal cluster of stars could stay together at that density, they would collide and fly apart. That logic narrows the options until the simplest explanation is a single, very compact object, a black hole, rather than some exotic swarm of unseen objects. Simple analogies help make the method less abstract. To weigh a hidden dog behind a fence, you might time how quickly its leash pulls a post around. To weigh a hidden black hole, you time how quickly stars orbit. There's even a touch of cosmic detective work. Precise measurements of star speeds, directions, and the tiny wobble of the radio source all act like fingerprints. And yes, astronomers sometimes joke that they're weighing something you can't put on a scale, but the math and the observations are stubbornly practical, and they keep pointing to the same hefty conclusion. The Event Horizon Telescope and the Shadow Image. Astronomers used a network of radio telescopes spread around the planet to capture the dark silhouette at the center of the Milky Way, turning many small dishes into one giant, planet-sized eye. They recorded radio waves instead of ordinary light because the gas and dust around the center block visible light but let radio waves pass through. The picture that came out shows a bright ring of glowing gas and a central dark patch, the shadow, caused by the black hole's extreme gravity bending and swallowing light. That ring isn't a literal rim, it's light from hot gas spiraling in, lit like embers around a furnace. To make a telescope as big as Earth, teams used a method that links dishes separated by continents, timing each observation with extremely precise clocks so the signals can be stitched together later. Think of it like asking people across the world to clap at the same exact beat and then lining up the claps to find the rhythm. When aligned correctly, the tiny differences add up to a very sharp picture. The raw data are enormous and messy, so powerful computers and clever algorithms are needed to sift through the noise, correct for the wobble of our atmosphere, and reconstruct the final image. It's part science, part art, and a bit like assembling a jigsaw puzzle where most pieces are invisible. The shadow itself is not a physical hole but the region where light paths are bent so strongly inward that photons cannot escape to our telescopes, so it appears dark against the glowing ring. Everyday examples help. Hold a flashlight behind your hand in a dim room and notice a darker area where light is blocked or scattered. Only gravity does the blocking around a black hole. The bright ring is also informative. Its shape and thickness give clues about how matter moves near the black hole and how fast that matter is orbiting. Small changes in the ring's brightness over minutes tell scientists that the environment is lively and chaotic, like traffic during rush hour near a toll booth. Creating the shadow image faced many hurdles, from weather at telescope sites to the fact that the black hole's feeding habits change quickly, which can blur the picture if observations aren't carefully timed. Teams cross-check results using different imaging methods so the final view isn't an artifact of any one technique. The achievement isn't just a pretty picture, it provides a practical test of how light and space behave under extreme gravity and helps refine models used to predict signals for future observations. And for those who like tasty metaphors, it's a cosmic donut whose hole teaches us as much as its glaze. Accretion disks, cosmic whirlpools of light. Gas and dust that drift too close to the Milky Way's central black hole don't fall straight in, they spiral, flatten, and form a wide, spinning disk. This band of material, called an accretion disk, is the stuff that feeds the black hole, and in the case of Sagittarius A*, the feeder is rather picky. The black hole itself has roughly 4 million times the Sun's mass, but it only gets a slow, leaky supply of gas. Think of the disk as a cosmic merry-go-round made of hot gas and tiny grains, where inner riders whip around much faster than those near the edge. A bathtub whirlpool gives the basic idea: things spiral inward because of angular momentum, not because something magical pulls them straight down. Friction and compression inside the disk turn orbital motion into heat, and that heat makes light. As the gas rubs and bumps and gets squeezed, it warms up until it glows in different kinds of light: radio waves, infrared, sometimes even 10th rays. If the disk were a campfire, most supermassive black holes burn like bonfires when they have lots to eat, but Sagittarius A* is more like a polite stove at low simmer. It shines, but not blindingly. A kitchen analogy helps: stirring a pot gently raises its temperature slowly, while rapid stirring can boil things quickly. The same basic cause and effect happens in the disk, only with magnetized gas and far stranger physics. The disk isn't a calm, uniform pancake. Inner parts whirl much faster and get far hotter than the outer parts, creating temperature and density differences that drive turbulence. Magnetic fields thread the gas and act like invisible rubber bands. When they snap or tangle, they can fling clumps of plasma outward or heat localized regions, producing sudden bright flares. Astronomers watching Sagittarius A* see these brief flares in infrared and 10th rays, which are like flickers from the stove when a bit of oil pops. Small, temporary hot regions can circle the black hole and make periodic blips in brightness, a bit like a car flashing by on a racetrack where the inner lanes are much quicker. Studying these disks gives practical clues about how black holes grow and how energy moves through a galaxy's core. Observations across many kinds of telescopes, radio dishes, infrared instruments, and 10th-ray satellites piece together a fuller picture of the disk's behavior, much like using different cameras to film a busy kitchen from above, the side, and through the oven door. Models and observations together tell us why disks around some black holes blaze brightly while others, like Sagittarius A*, keep a low profile. It all comes down to how much material arrives and how efficiently that material turns into light. In short, accretion disks are both simple in concept and endlessly complicated in detail, familiar as a spinning drain, and exotic enough to keep astronomers grinning like kids watching a slow-motion science trick. The mechanics of black hole feeding. At the heart of our galaxy sits an object with the mass of about 4 million suns, but it crowds that mass into a region only a few million kilometers across, roughly tens of times the radius of our sun. Gravity from something that compact creates a powerful pull that dominates the motion of nearby gas, dust, and stars. Observers see that material behaving as if being shepherded into tight orbits, sometimes slowly spiraling inward, and sometimes getting tossed away again. Fuel comes from everyday-sounding sources: winds from nearby stars, stray clouds of gas and dust drifting close enough to be tugged in, and occasionally a star ventures too near and gets stretched apart. Stellar winds are like a continuous puff from many tiny blowers. Together they create a windstorm of charged particles around the center. When those winds collide, they heat up and turn into a thin, hot soup of gas that the central object can grab. Think of it as crumbs and smoke being blown toward a campfire. You don't need a full delivery truck to keep the fire fed. Getting caught by gravity is only the first step. Most material has angular momentum, which is a fancy way of saying it wants to keep moving sideways instead of falling straight in. That sideways motion usually produces a spinning, flattened flow, a pancake of gas rotating around the hole, or a more puffy, hot swirl if conditions are sparse. Friction between neighboring layers, aided by tangled magnetic fields, works like rubbing your hands together. It turns ordered motion into heat. That heated gas shines in radio, infrared, and 10th rays, although not always brightly. Despite the enormous mass, the feeding process for this object is surprisingly stingy compared to the ravenous black holes seen in other galaxies. Much of the gas arriving near the center is too hot and too thin to radiate efficiently, so it slips in while hardly putting on a light show. Occasionally, magnetic fields snap and reconnect, unleashing short bursts of energy that make the center flare up briefly. These flare-ups are the astronomical equivalent of a sudden stove flare when you accidentally drop a spoon into a pan. Sometimes the menu changes dramatically when a dense cloud or a star gets too close. Strong tidal forces pull and stretch the unlucky object into streams of gas. This shredded material then circularizes and can feed the central object more rapidly for a while. Picture pulling a piece of taffy until it snaps, only the taffy gets flung into a spinning whirlpool. That temporary feast can light things up, but most of the time the feeding is a slow trickle rather than a banquet. In short, the mechanics of feeding here are a delicate ballet between gravity that wants to pull everything in, angular momentum that tries to keep it spinning away, friction and magnetic effects that convert motion into heat, and occasional violent encounters that dump fresh material into the central engine. It's cosmic dining with a complicated menu, a picky eater, and the occasional dramatic spill, no forks required, just physics and a touch of chaos. Magnetic fields and relativistic effects. High-resolution observations show that light coming from the immediate neighborhood of the black hole is polarized, which tells astronomers there are ordered magnetic fields threading that region. Polarized light behaves a bit like the glare reduced by polarized sunglasses. The way the light wiggles gives clues about the direction and strength of the magnetic field. In SGR-A*, those fields are not gentle like a fridge magnet, they are stretched and tangled by extreme motion and gravity, and they help shape how gas and particles move close to the black hole. Magnetic fields act on charged particles, forcing them to spiral and radiate energy as a steady glow. That kind of glow is the main source of the radio and infrared light we detect from SGR-A*. You can think of electrons moving along curved tracks like kids on a merry-go-round sliding outward and shouting, then the shouting is the light we see. Everyday analogies are handy. The way Earth's magnetic field channels particles toward the poles to make auroras is similar in principle, only on a vastly grander and wilder scale near the black hole. Relativistic effects become important because material near the black hole moves extremely fast and sits deep in a powerful gravity well. Time runs differently there compared with far away, clocks closer in tick more slowly. Engineers give GPS satellites tiny corrections for similar effects, though nowhere near the strength felt near a supermassive black hole. Light emitted close to the hole loses energy climbing out, shifting toward longer, redder wavelengths, a consequence of gravity's pull on light. The motion of orbiting gas also Doppler boosts the approaching side and dims the receding side, so one side can look brighter just because it's swinging toward us at a big fraction of the speed of light. Spin complicates things further. A spinning black hole drags space around with it, and that twisting motion winds up magnetic field lines like stirring honey with a spoon. The twisted fields can fling particles outward or channel flows into narrow streams. Whether SGR-A* produces a powerful, stable jet is still an open question, but weak outflows and flares are common, and magnetic twisting is a natural way to drive them. It's a bit like pulling on a rubber band, twisted enough and parts can snap outward. Combining both ideas, observers look at polarized light and rapid flares to read how magnetic fields and relativity work together. Polarization maps reveal whether fields are more ordered or chaotic, while rapid changes in brightness indicate material zipping around at relativistic speeds. These diagnostics are practical. They let scientists test models of how gas falls in, how some of it escapes, and how energy is converted into the light we detect. In short, magnetic fields steer the particles and light, and relativistic gravity and motion set the stage in which those fields are stretched, twisted, and sometimes victorious in launching particles back out into the galaxy, like a cosmic carnival ride where the rules of physics get stretched along with everything else. Relativity tested, gravity under extreme conditions. At the center of our galaxy sits Sagittarius A*, a very compact, very massive object that astronomers identify as a supermassive black hole. Its gravity is so strong that it dominates the motions of nearby stars and gas, creating a natural laboratory for testing Einstein's ideas about how mass bends space and slows time. In plain terms, general relativity says that big, heavy things warp the space around them, and clocks run differently depending on how deep they sit in that warped space. Near Sagittarius A*, the effect is dramatic enough to be measured with telescopes and precise instruments. Close-orbiting stars provide one of the clearest experiments. One bright star swings on a stretched path around the black hole, and as it makes its close path the light it emits is altered by gravity, shifted to redder colors, which we call gravitational redshift. Think of it like throwing a ball up a hill. The higher it climbs the less speed it has left when it gets to the top. Light climbing out of a gravity well loses energy in a similar way, and astronomers can measure that loss. The orbit itself also fails to repeat exactly like an old clockwork toy. Each lap the path shifts a little bit, just as if the track were slowly twisting under the runner. That small twist is exactly what curved space predicts. Telescopes that combine signals across continents add another kind of test. By linking radio dishes into a single, giant eye, astronomers can see the bright ring and dim center that mark the black hole's shadow, a silhouette formed against glowing gas. It's like watching a distant lighthouse through fog and seeing where the light is blocked. The size and shape of that shadow depend on how light bends near the hole, and the observed pattern matches what relativity predicts for such a compact mass. The hot gas orbiting there flares and flickers, sometimes looking brighter when it is coming toward us, which is a Doppler effect, the same reason an ambulance siren sounds higher-pitched as it approaches, and relativity helps calculate exactly how that brightness changes. Searching for precise clocks in tight orbits would sharpen the tests even more. Pulsars, rapidly pulsing neutron stars, act like cosmic metronomes, and finding one close to Sagittarius A* would let scientists measure tiny deviations in spacetime with extreme accuracy. It's like swapping a blurry kitchen timer for an atomic clock to time a race on a trampoline. The better the clock, the smaller the wrinkles you can see. For now, the observations available, stellar motions, light shifts, and the black hole silhouette, all agree with Einstein's predictions under these extreme conditions, though researchers keep looking for any hint of mismatch that would point to new physics. Practical examples from everyday life help keep this grounded. The global positioning system must correct satellite clocks for both motion and gravity, or your navigation app would quickly steer you into a ditch. Relativity is not just a space oddity. And if someone accuses you of bending the truth, you can joke that spacetime handles bending much better than some people handle bending the rules. In short, gravity near Sagittarius A* gives scientists one of the toughest reality checks for relativity, and so far the theory keeps passing with flying colors, or at least with the expected redshift. Jets, winds, and galactic weather. Sagittarius A* sits at the center of our galaxy and contains roughly 4 million times the mass of the Sun, while lying about 26.0 light-years from Earth. It does not glow like the brightest black holes in other galaxies, instead it is relatively dim, but it still stirs up interesting activity in its neighborhood. Astronomers detect bursts of light in 10th rays and infrared coming from near it, which tell us that gas and particles around the black hole sometimes heat up and flare. Instruments that watch the sky in radio, infrared, and 10th rays catch these changes and help map how material moves and reacts close to the black hole. Jets are narrow streams of particles that some black holes shoot out like cosmic fire hoses, formed when spinning gas and magnetic fields channel matter away from the center. For Sagittarius A*, any jet activity is weak and elusive compared with the dramatic jets seen in active galaxies, but there are hints, faint, elongated features seen in radio or 10th ray maps that suggest small outflows. Think of it as the difference between a garden hose that shoots water across the lawn and a high-pressure fire hose. SGR A* at best flicks a wet finger of plasma rather than blasting a stream across town. Those tiny streams still matter because even a subtle, focused outflow can nudge nearby gas and change where new stars might form. Winds near the galactic center are a different kind of breath, fast, hot flows driven by hot gas and by the strong winds of massive stars that crowd the central region. These stellar winds act like a million tiny hairdryers, feeding hot material into the neighborhood and stirring up turbulence. The black hole tries to eat, but the wind can blow the meal away. This makes the feeding process messy and inefficient. There is also a ring of gas and dust orbiting the center, often called the circumnuclear disk, which serves like a pantry full of ingredients. Sometimes items fall in, sometimes they get pushed around by gusts and flares. Galactic weather is the handy phrase astronomers use to describe all this activity: flares, gentle jets, chaotic winds, and pockets of hot gas all interacting in a dynamic way. Short bursts of 10th rays are like lightning flashes. They heat nearby gas and can ionize it, changing its chemistry. Over time, outflows and winds can sweep gas away from the center or compress clouds and trigger star formation, just as a strong wind can scatter leaves or push them into a pile. Observations across different wavelengths let scientists trace these processes. Radio telescopes map cold gas structures, infrared sees warm dust and stars, and 10th-ray observatories show the hottest regions, so astronomers can read the changing weather forecast for the Milky Way's core. Practical consequences of this galactic weather are subtle but real. Because Sagittarius A* is not force-feeding on large amounts of material, the central region is quieter and more hospitable for delicate structures like stars and dense clouds. Extreme jets and winds would clear out the area and shut down star formation. Yet occasional flares and small outflows can still sculpt the central environment, nudging gas streams and altering orbits. In everyday terms, SGR-A* behaves less like a roaring furnace and more like a temperamental stove that sometimes pops, inconvenient if you're cooking, but not catastrophic. Researchers continue to watch, and the picture keeps improving as instruments get sharper. Small hints in radio images and sudden 10th-ray spikes are pieces of a larger puzzle about how jets and winds interact with the galactic center. It's a complex choreography of pushes and pulls, with magnetic fields, hot winds, and the black hole's gravity all playing roles. Think of it as a cosmic weather report that changes on short timescales and keeps astronomers checking the skies, and occasionally laughing at how even a supermassive black hole can have mood swings. Why Sagittarius A* is so quiet? At the center of our galaxy sits a supermassive object about 4 million times the mass of the Sun, yet it gives off surprisingly little light compared with many other cosmic monsters. In simple terms, brightness comes from stuff falling into a black hole and heating up as it scrapes and smashes on the way in. If there is not much stuff, or that stuff is mostly hot and thin, the whole process barely glows. Think of a huge stove that looks impressive but is left on the lowest setting. You know it's powerful, but it won't toast your bread. One big reason for the silence is a shortage of easy snacks. The stars near the center do shed gas, like people blowing off steam, but much of that gas never makes a straight trip into the black hole. Gas needs to lose a lot of its sideways motion, its go-round momentum, before it can fall in, and that doesn't happen efficiently here. Picture a merry-go-round full of marbles. Most marbles roll around and around instead of dropping down a hole in the middle. Because the supply is sporadic and thin, the black hole often sits with little to munch on. Another reason is the way the available gas behaves. Near the black hole the gas is extremely hot and very spread out, so its particles slam around without forming a dense, bright disk. When material is dense and cool, it radiates lots of light as it spirals in, like wood crackling brightly in a campfire. When it's hot and sparse, energy goes into heating and fast motion rather than shining, more like embers that glow faintly. Magnetic fields and winds can also fling energy and matter away before it gets down the chute, acting like someone constantly sweeping crumbs off the table so the eater never gets full. In other words, energy is often carried off as motion or heat instead of being released as visible light. Astronomers do see occasional outbursts, though, brief moments when the center flares up in 10th rays and infrared. These flashes last for tens of minutes to a few hours, and they probably come from small clumps of gas or blobs of plasma that suddenly make it close enough to light up. It's like the quiet neighbor who suddenly throws a tiny party when a pizza delivery arrives. Those flares give scientists useful clues, because a quiet background lets brief events stand out clearly in observations. Finally, the environment itself helps keep things calm. Stars and their winds interact in complex ways, scattering gas into chaotic orbits rather than delivering a steady stream. The result is a neighborhood where material either escapes, circles for a long time, or gets blown away, none of which is good for a steady, bright feed. This quiet behavior is not a sign of weakness, it just means the black hole is picky about how it eats. And for observers on Earth, that pickiness is a blessing, because it makes studying the black hole's rare outbursts and the physics around it much easier, like being able to hear a whisper in an otherwise silent room. Tidal disruptions, when stars get too close. When a star wanders too close to the supermassive black hole at the center of the Milky Way, the difference in gravity from one side of the star to the other can stretch and tear it apart. This difference is called a tidal force, and it works like the same pull that raises tides on Earth, only much, much stronger. Think of ocean tides on steroids. The star's outer layers can be peeled off while its core may be stretched into a thin stream of gas, a process often nicknamed spaghettification by scientists, which is as silly as it sounds and oddly accurate. As the star is torn, some of the shredded gas falls inward and some is flung outward. The inward falling gas can swirl around the black hole, forming a hot, glowing disk that shines in 10th rays, ultraviolet and infrared light. That bright flare is how astronomers know something dramatic happened, because the black hole suddenly turns on, in wavelengths where it was quiet before. In many cases the star is not completely destroyed, it can lose a chunk of mass and keep orbiting, altered and battered, rather like a cookie with a big bite taken out of it that still manages to tumble around the plate. Observationally, these disruptions make themselves known by sudden brightening and unusual emissions across multiple wavelengths, and sometimes by streams of debris that later light up surrounding dust, a delayed glow known as a dust echo. Telescopes that see 10th rays, infrared light, and radio waves are all part of the detective team that pieces the story together. Occasionally a disruption launches a narrow beam of particles at very high speed, similar to a cosmic fire hose. When that happens the event can be even more dramatic and visible from far away. The consequences are both violent and informative. The black hole gets a short-lived meal, growing a little and flaring up, while the star may be left wounded and on a new, tighter orbit. Such encounters are rare in our galaxy but are hugely valuable to scientists because they expose how matter behaves under extreme gravity and heat. For the rest of us, it's a reminder that space is not just empty and quiet. Sometimes it's a place where stars get pulled like taffy, and astronomers get to watch the cosmic dessert being made. Star formation in the shadow of a giant. The center of our galaxy is dominated by a giant, hungry object surrounded by clouds of gas and clusters of stars, and yet surprisingly, new stars are still being born there. Close to that giant, astronomers have found young stars moving in tight orbits and groups of massive, hot stars arranged in disk-like patterns. These discoveries show that star birth can take place even where conditions seem most hostile. Near the giant, gravity is so strong that it stretches and pulls on clouds of gas, making it hard for them to hold together and collapse into stars. Radiation and fierce winds from nearby massive stars add extra punishment, blowing material away like a leaf blower on a pile of snow. Think of trying to build a sandcastle right at the edge of a crashing wave. The same forces that make the spot dramatic also make it a bad place to keep your tower intact. Despite all that, pockets of gas sometimes get compressed enough to spark collapse. Collisions between gas streams, or the formation of a dense, spinning disk of material, can create regions where gravity wins out. Simple, everyday pressure helps explain this. When you squeeze a sponge in your hand it gets denser. In the galactic center, squeezing comes from crashes of clouds and the overall squeeze of gravity. Short bursts of calm can follow violent events, and in those moments, a new star can take shape. These newborns are often big and bright, like teenagers that burn fast and live loud. Astronomers point to several real examples that make this story concrete. Close-in stars, sometimes called S-stars, orbit only a short distance from the giant, showing that young stars can survive in tight neighborhoods. A bit farther out, dense star clusters contain many massive, young suns packed together, proving that clouds can fragment and form whole families of stars even under pressure. Observations also show disks of young stars circling in the same direction, which supports the idea that a rotating flow of gas can break into pieces that become stars. This unusual star formation changes both the stars and the giant that shadows them. Massive newborn stars shine hard and later explode, stirring the gas and sometimes feeding or starving the central object. Studying these processes gives scientists a natural laboratory for extreme physics, like watching baking experiments in a pressure cooker instead of your home oven. It's messy, energetic, occasionally loud in cosmic terms, and a little bit amusing that life, even stellar life, finds ways to start in the most forbidding places. Simulating the center, virtual laboratories. Sagittarius A* is the bright radio source at the center of our galaxy, and it contains a black hole about 4 million times the mass of the Sun, and scientists build virtual laboratories, computer simulations, to reproduce what happens near it. These simulations solve how gas moves, how magnetic fields twist, and how light bends in a strong gravity environment. Think of it as a very detailed movie made from equations. The purpose is straightforward: connect what telescopes see to the physical processes near the hole, so observations stop being mysterious and start being useful. Simulations use two basic tricks to represent the messy gas around the black hole. Either space is sliced into many tiny boxes where equations are solved, or the motion of many particles is tracked like grains of sand in a wind tunnel. Magnetic fields are added because they act like invisible elastic bands that can fling gas outward or heat it up. A simple kitchen example helps. Stirring milk into coffee makes swirling patterns that look a lot like the flows in an accretion disk, only the black hole's gravity makes the swirl far more dramatic. To turn the physics into pictures, models also calculate how light travels through the curved space, producing synthetic images and light curves that can be compared directly with telescope data. These virtual labs have practical uses. They help explain sudden bright flashes, called flares, as hot clumps of gas orbiting close to the black hole, or as magnetic fields snapping and releasing energy, rather like sudden sparks when you unplug a charger. Simulations also predict polarization patterns, how light wiggles, which observers can measure to learn about magnetic field directions. Observers and modelers talk to each other. A simulation might suggest looking at a certain radio wavelength for a particular signature, and telescopes like the Event Horizon Telescope or 10th Ray observatories can test that prediction. Think of it as weather forecasting for the galactic center. You can't step outside and measure the storm directly, but models help you decide when to take an umbrella. There are limits, of course. Running a detailed virtual lab requires lots of computer power, so choices must be made about what to include and what to simplify. Microphysics, like how particles accelerate or collide, is often approximated. Improvements in hardware, clever algorithms, and better input from larger-scale galaxy simulations are gradually closing the gap, like upgrading from a pocket calculator to a gaming PC for physics. The end result is a toolkit that lets scientists run controlled experiments on the computer, test ideas about gravity and plasma behavior, and explain real observations with surprising clarity, and occasionally a little cosmic humor when a simulated hot spot looks suspiciously like a tiny galactic donut. Multi-wavelength astronomy, a symphony of light. At the center of the Milky Way sits a compact beast about 4 million times the mass of the Sun, and astronomers study it by collecting many kinds of light at once. Different parts of the light spectrum are like different cameras that each pick up their own story. Radio waves cut through the thick clouds of dust that hide the galactic center, infrared reveals warm gas and the stars threading close by, 10th rays flash when hot bits of gas get turbocharged, and high-energy gamma rays point to the most extreme particle fireworks. Together these views create a fuller picture, the way listening to an orchestra gives more detail than hearing just the violin. Radio telescopes act like long-wavelength glasses that peer right through the dust. Arrays such as the Very Large Array and ALMA combine many dishes to map cold gas and the larger-scale flow of material. Very long baseline networks, including the Event Horizon Telescope, link dishes across continents so they behave like a single enormous dish and can resolve the shadow-like silhouette of the black hole. Think of radio observations as using a fog lamp on a March night. You can't see all the colors, but you can find the road and spot the big shapes. The technique that stitches far-apart telescopes together is a clever trick. It's like synchronizing dozens of watches to take one giant snapshot, and that lets astronomers see structures as small as the region right around the black hole's edge. Infrared light tells a complementary story because it reveals heat. Telescopes with adaptive optics, like those on large ground-based observatories, watch individual stars swing close to the center and track clouds of warm gas. Infrared flares come and go, and they often accompany 10th-ray flares, which suggests the same particles or processes are responsible. A practical analogy is a city at night. Infrared shows the heated rooftops and lit windows that are invisible when you only look in visible light. When something nearby suddenly heats up, infrared cameras pick that up fast, giving clues about where matter is getting squeezed, heated, or shoved around. 10th rays are the trumpets for sudden energetic events. Space telescopes tuned to 10th rays, such as Chandra and XMM Newton, catch bright bursts when material near the black hole is rapidly heated or when magnetic fields snap and release energy. These 10th-ray outbursts can be brief but intense, and they often line up with infrared flickers, hinting at a linked cause. If infrared is the glow of a skillet warming on a stove, 10th rays are the moment a flick of the flame sends a flare of sparks, brief and telling. Observing the timing between infrared and 10th-ray spikes helps astronomers figure out whether particles are being accelerated in place or are being flung outward and cooling as they travel. At the highest energies, gamma-ray instruments and ground-based Cherenkov telescopes search for the most extreme particles and tiny, fast blasts. Not every telescope sees the same events, because some processes create mostly low-energy light while others produce the high-energy photons. This is why coordinated campaigns are so valuable. Catching a flare across radio, infrared, 10th ray, and gamma-ray bands can pin down where it started and how energy moves. In everyday terms, it's like watching a neighborhood party from different windows. One window shows the barbecue, another shows people dancing, and a third captures the DJ's flashing lights. Each viewpoint is true, but only together do they reveal the whole scene. Coordinated observations also reveal delays and lags between bands, which act like a cosmic stopwatch. Sometimes an infrared flare is followed a little later by a radio brightening, which can mean a blob of hot plasma expanded and cooled as it moved outward. That lag gives a handle on size and speed, without ever touching the gas. Simple experiments at a barbecue illustrate this. You see the smoke rise, then later smell the barbecue. Sight comes before smell because of how the air moves and how each sense picks up different signals. Similarly, light at different wavelengths arrives in patterns shaped by motion, temperature, and magnetic forces. Putting these pieces together keeps the story grounded in real physics without requiring a single instrument to tell everything. Each wavelength probes different scales and conditions, much like having both a wide-angle lens and a magnifying glass for the same scene. The mix of instruments, careful timing, and a little ingenuity lets astronomers decode events around the black hole, and occasionally enjoy the cosmic equivalent of fireworks, minus the neighborhood noise complaints. Timescales and cosmic history. The heart of our galaxy ticks on many clocks at once. Some beats are quick and dramatic, while others crawl on a timescale that would make a glacier impatient. Close to the black hole, gas and magnetic fields sometimes produce sudden flashes of light, bursts that rise and fall in minutes to hours. These brief flares are like the sudden bright pop of a firecracker, compared with the slow glow of a campfire. They come from materials swarming very near the black hole's edge, heating up and then cooling almost as quickly. At longer wavelengths, such as radio waves, the brightness can wander over days to months, much like the varying hum of a city that's quieter at dawn and louder by afternoon rush hour. The stars that orbit nearby offer a different kind of clock, one that ticks predictably and helps set the scene for longer stories. One famous star swings around the center in a time you could measure in human decades, about 16 years for a full lap, so careful watching of these orbits tells astronomers how heavy and how quiet or busy the center really is. Other stars take much longer to complete their journeys, and gas clouds and dust can drift inward over years to centuries, lending the center a slow, weather-like rhythm. Think of it like traffic patterns around a roundabout. Motorbikes dart quickly, buses make slow loops, and occasionally a truck loads the road for a long while. Over still longer stretches of time, the black hole's mood can shift from sleepy to lively and back again. Compared with the extremely bright, active black holes seen in some other galaxies, our central black hole is mostly calm now, more ember than roaring bonfire. But traces around the galaxy, such as big bubbles and moving gas, act like fossilized smoke. They hint that the center has been more energetic in the past. These changes play out on timescales of thousands up to millions of years, and their impact on nearby star formation and gas distribution is similar to how a seasonal storm reshapes a coastline. The landscape of star birth can be boosted or stifled depending on how much energy is dumped into the neighborhood. Looking at the longest horizons, black holes grow and evolve over millions to billions of years through slow feeding and through collisions with other black holes when galaxies merge. This is the kind of growth that's less like dieting and more like compound interest. Small, steady gains can add up to dramatic change given enough time. The history encoded in timescales helps astronomers place our quiet center within the broader life story of galaxies. It explains why some galactic centers are bright beacons while others, like ours, prefer a low-key existence. And yes, patience is part of the job. Watching these cosmic clocks requires a willingness to follow events that unfold on schedules far longer than a human lifespan, which is both humbling and oddly comforting. Interactions with gas clouds and stellar clusters. At the very center of the Milky Way there is a compact, extremely heavy object surrounded by a busy neighborhood of gas and stars, and that neighborhood never sits still. Thick clumps of gas drift in from farther out, sometimes forming a donut-shaped ring, while tight groups of young, massive stars sweep around on fast paths much closer in. These stars shed material through strong stellar winds, and that outflow of gas acts like a slow drizzle that can feed the center when conditions let it. Think of it as a city center where delivery trucks, pedestrians, and wind gusts all crowd a roundabout. A few stray packages occasionally get dumped toward the middle. When a loose cloud of gas wanders too near, the central gravity stretches and squeezes it. The effect is a bit like pulling and stretching taffy. One side is tugged harder than the other, and the cloud can be torn apart, heated, and stirred into a hot glow. Sometimes the cloud is compact enough to survive the close pass, and then it behaves like a wet sponge squeezed by a giant hand, releasing gas that can fall inward. That falling gas often lights up. Astronomers see sudden flares in infrared and 10th-ray light as the black hole briefly feeds. Picture a usually calm campfire that suddenly flares when someone throws on a handful of dry kindling. The light spikes and then dies back down. Stars in the innermost region play a double role. Their tight, fast orbits act like test particles that reveal how heavy and compact the central object must be. By watching their paths, scientists can measure the mass without touching it. At the same time, massive stars blow powerful winds and sometimes die in explosive events, sending shells and clumps of matter outward. Those ejecta can collide with other gas and with the ambient medium, creating shocks and heating that gas further and sometimes sending new material spiraling inward. A simple life example: imagine a busy street fair where people occasionally bump into food stalls and knock over boxes. Scattered snacks then end up underfoot, and a hungry dog might dart in to snatch them. Chaos yields new short-lived opportunities. The continuous exchange between the central object and its surroundings creates a feedback loop that shapes the environment. If the central source lights up strongly, its radiation and outflows heat the nearby gas and can keep it from collapsing into new stars, like a nearby heater melting snow and preventing it from building up. Conversely, compression from shocks and passing clouds can squeeze gas into denser clumps and trigger star formation in pockets, comparable to someone pressing dough into a loaf. Keeping track of these interactions, by watching radio waves, infrared glow, and high-energy flashes, lets astronomers see how feeding events unfold and how the galactic center evolves. And yes, sometimes it behaves like a picky diner that only nibbles small bites. Other times it makes a mess and the whole kitchen lights up. Surprises from the galactic center. Telescopes aimed at the center of the Milky Way keep turning up sudden bursts of light and energy that scientists did not fully expect, and those bursts have taught us a lot. These flashes show up in 10th rays, infrared, and radio waves, and they come and go on timescales of minutes to hours, which is surprisingly fast for something so massive. Think of it like a campfire that usually smolders quietly but sometimes sends up an unexpected flare when a new log shifts. The flare tells you about the fuel and the way air moves through the wood. In the same way, the behavior of these flares tells astronomers about hot gas. magnetic fields, and how matter moves right near the black hole. Close to that compact object, stars orbit in tight, swooping paths that are both useful and puzzling. By tracking those star orbits, scientists confirm there is a single, very dense object controlling them. The motions are like dancers swerving around a single, invisible partner. What was odd was finding relatively young, massive stars so near that partner, because the strong pull there should make it hard for stars to form. It's like finding a playground full of toddlers inside a spinning blender. You wouldn't expect them to get a chance to grow up there. That puzzle forced astronomers to rethink how stars might be born in extreme places, or how they might migrate inward after forming farther out. Another surprise came from a cloud of gas and dust that approached the center and didn't do what many people predicted. Instead of being shredded completely, it held together more than expected and may be hiding a star inside. That outcome suggested some of these objects are more complicated than a simple blob and that the black hole's feeding habits are not just a steady drizzle. Also, astronomers had hoped to find many spinning neutron stars, called pulsars, near the center because they would act like precise clocks and probes. Instead, there were very few, until a highly magnetized neutron star, a magnetar, turned up close by. That discovery was a useful surprise since magnetars are noisy but bright signposts, helping measure magnetic fields and the fog of charged particles between us and the center. The lack of many pulsars remains a mystery, like expecting a crowded bus stop and finding only one or two people waiting. On larger scales, the galactic center has left even grander clues that it can behave wildly. Huge, bubble-like structures reach far above and below the plane of the galaxy, glowing in high-energy light. They look like giant smoke rings blown by some energetic event at the center long ago. More recently, very detailed radio observations have given us an image of the compact region near the black hole, revealing a churning, turbulent flow of plasma and shadow-like features that match the idea of light being bent by extreme gravity. All of this changed the simple picture of a constantly quiet, sleepy center. Instead, we see a mostly calm beast that can wake up, spit out energy, and leave lasting marks on its surroundings. That kind of behavior matters for the whole galaxy because outbursts from the center can heat gas, influence star formation, and reshape the environment on scales much larger than the black hole itself, a small but fierce troublemaker with a long reach. Instruments and techniques that made it possible. Radio, infrared, and 10th-ray observatories work together like different-sized lenses on a huge camera to reveal the center of our galaxy. Radio dishes pick up long-wavelength light that sails through the dusty plane of the Milky Way, while near-infrared instruments see stars that are hidden in visible light, and 10th-ray telescopes catch sudden, energetic flares. Each type of telescope answers a different question, so scientists use them as a team rather than relying on one tool alone. Very long baseline interferometry, or VLBI, is a trick that turns many separate radio telescopes into a single, giant telescope by combining their signals. Think of it as using many small mirrors to act like one huge mirror, giving much finer detail than any single dish could. To do this, each telescope records radio waves with extremely precise clocks. Later the recordings are brought together and aligned, so the tiny timing differences become information about fine structure. The Event Horizon Telescope used this idea to make an image of the immediate surroundings of a black hole, and arrays like ALMA provide the sensitivity needed by VLBI to detect faint millimeter-wave signals. Adaptive optics is what lets ground-based infrared telescopes see almost as sharply as space telescopes. Turbulence in Earth's atmosphere blurs starlight, like trying to read a text message while your hand trembles. Adaptive optics measures that blur in real time and bends a mirror to cancel it, restoring a crisp image. Instruments at large observatories, such as the Very Large Telescope and the Keck telescopes, use this method to track stars moving around the galactic center. The gravity instrument takes it further by combining light from several telescopes to measure positions extremely precisely, which is how astronomers can map stellar orbits near the center and test how gravity behaves there. Spectroscopy and precise timing are simple ideas with powerful results. Splitting light into its colors reveals motion through the Doppler effect. Light shifted toward the red when something moves away, and toward the blue when it moves closer, just like the changing pitch of a passing siren. This lets astronomers measure how fast stars near the center are moving. Time-domain monitoring with 10th-ray and infrared telescopes catches sudden flares and variability, offering insight into energetic processes near the black hole's edge. Polarization measurements add another layer by revealing the orientation of magnetic fields, similar to how iron filings show us the invisible pattern around a magnet. All of this depends on heavy-duty data processing. Raw signals are noisy and incomplete, so researchers use image reconstruction algorithms to stitch the data into pictures and maps. It's a bit like stacking many slightly blurred photos from a shaky hand to make one clear image, except the software is far less forgiving and you can't just ask your camera to take another shot. Calibration techniques, error cancellation methods, and statistical modeling are essential, and they let small but real signals emerge from messy observational data. The result is a steady stream of usable measurements rather than a single dramatic snapshot. Finally, teamwork between observatories and methods is crucial. Coordinated campaigns combine radio VLBI, millimeter arrays, infrared interferometry, and 10th-ray observatories to capture different behaviors at the same time. That coordination resembles a well-orchestrated potluck where each dish matters. Miss one contribution and the full picture is incomplete. Small telescopes contribute monitoring, large arrays provide resolution, and specialized instruments like interferometers and adaptive optics provide the precision. Together they make the center of our galaxy accessible to human curiosity, with a little help from clever engineering and a lot of computer muscle. The next decade, upcoming missions and telescopes. Several major observatories and instrument upgrades are being built or expanded to give a much clearer view of Sagittarius A*, and that means sharper pictures, better timing, and more ways to listen to its tiny, wild neighborhood. The Event Horizon Telescope is not done improving. Plans to add more radio dishes and to coordinate them better aim to turn the network into a far bigger, more sensitive array. Think of it like turning a group of backyard cameras into a giant movie camera by syncing them perfectly. Suddenly you can watch fine details that used to be fuzzy. This helps astronomers image the immediate surroundings of the black hole and follow fast changes that might last only minutes. Infrared telescopes on the ground are also getting major upgrades that will let scientists follow the dance of stars close to the black hole with far greater clarity. Extremely large mirrors and better correction for Earth's wobbly air, called adaptive optics, which is just a fancy way of saying smart mirrors that cancel the blur, will let researchers track star orbits and glowing gas in more detail. It's like switching from a phone camera to a high-end DSLR when photographing a fast-moving bird. You get sharper shapes and can tell if the bird is annoyed or just hungry. Instruments designed to split light into its colors will reveal the composition and speed of gas, which helps show how matter is falling in or being tossed away. On the radio side, new arrays such as a next-generation very large array and the square-kilometer array will give much more sensitive and flexible ways to study the low-frequency radio waves coming from near the black hole. Radio telescopes are good at catching steady hums and sudden flares. Adding many more antennas is like putting up a massive network of ears across a continent so nothing gets missed. This will help scientists detect faint pulses from potential neutron stars near the center and map how jets or outflows move and change. The black hole surroundings don't always shout, more often they whisper, and these instruments are being tuned to hear those whispers. 10th-ray observatories planned for the coming years will focus on the hottest, most energetic parts of the environment, where gas gets heated to millions of degrees and lights up in 10th rays. 10th-ray detectors are like thermal goggles that can see the hottest parts of a bonfire from far away, showing where dramatic heating or sudden flares happen. Combining those 10th-ray views with the radio and infrared data creates a fuller picture. One instrument may see a flare begin while another watches how the gas reacts, and together they tell a cause and effect story. This multi-wavelength teamwork is practical and powerful. It helps distinguish whether a brightening is caused by magnetic activity, by material falling in, or by something else entirely. Upgrades to instruments that measure tiny changes in the position and speed of gas and stars, such as interferometers that combine light from several telescopes, will sharpen tests of how gravity behaves in extreme conditions. Simple tools like better clocks and faster computers are also a big part of the story, because enormous amounts of data must be aligned, compared, and analyzed. Imagine trying to follow dozens of video feeds of a busy street at once. You need both storage and smart software to pick out a single red bicycle. Expect to see machine learning and advanced pipelines used more often to sift through the avalanche of information, which keeps the process practical and makes discoveries faster, and yes, slightly more like detective work than pure staring at pictures. All of these projects together will make observations of Sagittarius A* far more routine and much richer. Instead of a few dramatic snapshots, astronomers will get movies in different kinds of light, sensitive measurements of changing magnetic fields and gas flows, and better chances to spot rare events. The payoff is a much clearer sense of how the black hole eats, coughs, and influences its neighborhood, told through coordinated observations that are part concerted stakeout and part scientific pep rally. The coming instruments won't give every answer, but they will hand scientists far better clues, and who doesn't like better clues? Scientific debates and alternative ideas. Astronomers watch stars whipping around the center of our galaxy, and those motions are the main reason most scientists think there is a very compact, very heavy object there. That conclusion comes from how tightly the stars curve in their paths and how fast they move when they swing close to the center. Observations also show bursts of energy in radio and 10th rays and a compact radio source that sits essentially where those stars loop around. These pieces of evidence point towards something small and extremely dense, but they do not, by themselves, force everyone to call it a black hole. Some researchers have suggested other possibilities. One idea is a dense swarm of dark objects, things like neutron stars or small black holes packed together so tightly they mimic one big mass. It sounds a bit like a swarm of gnats that, from far away, looks like a single insect. But in practice, such a cluster would collide and break apart over time, and would likely glow differently than what we actually see. Another proposal involves exotic particles forming a smooth, star-like lump, a so-called boson star or Fermion ball, which would be compact without an event horizon. Those models can be tuned to match some observations, yet they require types of matter we have not yet confirmed in the lab. The sharpest tests come from how light and gas behave near the center. Very short bursts of brightness suggest that processes happen in an incredibly small region. The Event Horizon Telescope's image of a bright ring surrounding a darker area is especially hard to explain without something that acts like an event horizon, a boundary beyond which light cannot escape. That image resembles the shadow predicted when light bends around an object with extreme gravity. Alternatives must reproduce that ring and its size, and not many do so naturally. In other words, an imposter would need to be a pretty convincing liar to fool all the instruments at once. Still, not every question is settled, and debates persist about why this object is so quiet compared with the powerful black holes that light up other galaxies. Some scientists argue the feeding process is different here. The gas is thin and inefficient at turning motion into light. Think of it as a campfire that only gets a few twigs instead of a full log. Others suggest magnetic fields and winds fling matter away before it can fall in, which makes the center look faint. Each model explains some observations but not all, so the discussion continues. There is also room for truly out-there ideas, like a gateway to another region of space or a gravistar that replaces the interior of a black hole with a different form of spacetime. These are imaginative and fun to consider, and they keep theorists on their toes. Yet they often demand new physics or very precise conditions, which makes them less favored until someone finds clear evidence that standard explanations fail. Practical tests will keep narrowing the options. Better images, more precise tracking of stellar orbits, and improved measurements of flares and polarized light act like different detective tools. Each new observation either makes the black hole picture cleaner or forces alternatives to produce ever more complicated stories. For now, the simplest answer, an extremely compact object behaving like a black hole, fits the bulk of evidence, but science stays healthy because some scientists keep asking awkward questions and proposing wild ideas. After all, without a few contrarians, astronomy would be just a bunch of quiet stargazers agreeing with each other. Public fascination and pop culture echoes. The center of our galaxy is a source of steady public curiosity, and that curiosity often turns into stories, images, and jokes that spread far beyond science magazines. At its core sits an object so compact and heavy that its gravity keeps light from escaping. People tend to picture it as a cosmic drain, though in reality it behaves more like a very strong, very local gravity well. Popular attention grew as observatories and filmmakers began showing what such an extreme environment might look like, and those images and visual effects stuck in the public mind. Filmmakers lean on the mystery because it makes great cinema. A well-known movie used careful scientific advice to create a black hole that looked believable on screen, and the unusual visuals, warped light, glowing rings, made for memorable posters and water-cooler conversation. Television shows and science documentaries borrow the same imagery, sometimes stretching the facts for drama, and video games use exaggerated versions as wormholes, shortcuts, or final bosses. Real-world planetarium shows often recreate the experience with surround sound and sweeping visuals, and that immersive approach helps people feel close to something that, in reality, is many light-years away. Science communicators and casual fans meet in the middle through social media, podcasts, museum exhibits, and merch. Animations and radio telescope images shared online convert confusing data into a single striking picture, so t-shirts, coffee mugs, and posters with stylized black holes proliferate. Amateur photographers capture the bright band of the Milky Way across a night sky and point out roughly where the galactic center lies, no telescope required to appreciate the view, while children draw big black circles with crayons and call them space monsters. That blend of serious research and everyday culture keeps the topic alive in classrooms and cafes alike. The idea has slipped into language, too. People call debt, bureaucracy, or bad relationships a black hole, and the term conveys absence, danger, and the unknown in a single punchy phrase. Musicians and visual artists borrow the concept for mood and metaphor, turning scientific wonder into personal feeling. Misunderstandings persist. People sometimes think of black holes as roaming vacuum cleaners, so popular representations also shape what needs correcting. Educators use those moments to explain calmly and with a smile that black holes don't go around naively gulping everything in sight. In short, the mix of real observations, dramatic imagery, and everyday jokes has turned the galactic center from a remote scientific subject into a familiar cultural touchstone, equal parts awe and amusement. Communicating the cosmos, outreach stories. The center of our galaxy hides a compact radio source called Sagittarius A*, which is tied to an enormous black hole. That black hole is not a vacuum cleaner roaming space looking for socks, it's a region so dense that even light struggles to escape, and scientists study it by listening to faint radio signals and tracing the motion of nearby stars. Outreach teams turn those radio whispers and star motions into stories people could hold, using images, animations, and hands-on activities to make the unseen feel familiar. Communication started by translating complex techniques into everyday language. The Event Horizon Telescope, a network of radio dishes that act like one giant telescope, produced images that outreach teams turned into clear visuals and short films. Planetariums and science centers used these visuals in full-dome shows so audiences could feel as if they were flying toward the galactic center. Teachers took the same idea into classrooms. A stretched sheet with marbles shows how heavy things bend space, and a flashlight through fog helps explain how astronomers detect objects they cannot see directly. Simple, interactive examples work well because they let people try things with their hands. Scientists also took to social media, podcasts, and live question-and-answer sessions to answer curiosity in real time. A short video that compares a black hole's pull to a drain in a bathtub gets more attention than a long technical lecture. Citizen science platforms invited the public to help identify patterns in radio images and galaxy surveys, making people actual participants rather than passive viewers. Museums paired the data with artwork and music, turning radio signals into soundscapes, for instance, so that people who relate to art rather than equations could find an entry point. It's surprising how well a good soundtrack helps explain a gravity storm, plus it's a lot less dusty than a physics textbook. Honesty about uncertainty became a central lesson in Outreach. The public was shown that images are reconstructions made from many radio measurements and clever algorithms, not straightforward snapshots, and that fits a useful real-world analogy. It's like building a portrait from grainy security camera clips rather than taking a single selfie. That kind of transparency builds trust. Outreach that mixes clear metaphors, hands-on demos, and accessible visuals tends to spark the most curiosity. Keep explanations short sometimes and long sometimes, depending on the moment. A well-timed joke, black holes aren't great house guests, they never leave, helps, too. Local initiatives matter a lot. Small astronomy clubs bring telescopes to parks. Libraries host talks where people can ask practical questions about what a black hole does to nearby stars. Classrooms use everyday objects, coins, rubber sheets, toy cars, to demonstrate orbital motion. These examples show that communicating the cosmos is not just about grand press events and big images, it's also about the tiny, repeated moments when someone connects a simple demo to a sweeping idea. Outreach is both rocket fuel and duct tape. It needs inspiration and it needs practical tools to keep people engaged. Finally, the most effective stories focus on human curiosity and process. Instead of claiming absolute certainty, communicators explain how teams test ideas, compare methods, and sometimes disagree before reaching a consensus. Real-world comparisons, like assembling a puzzle from blurred pieces or using many small cameras to make a single panorama, help people appreciate the work without drowning them in jargon. With clear language, playful demonstrations, and a touch of humor, stories about Sagittarius A** bring the edge of the galaxy a little closer to everyday life. Big questions that remain. Sagittarius A** sits at the Milky Way's center and contains a supermassive black hole weighing roughly 4 million times the mass of the Sun, but how it behaves still raises a lot of questions. Astronomers can watch gas, dust, and nearby stars move under its pull, and they see sudden bursts of light now and then, yet we do not fully understand why those bursts happen. The black hole itself is surprisingly quiet compared with the bright, eating machine seen in other galaxies, and figuring out what makes it so calm is a central puzzle. One big question is how material actually gets from the surrounding galaxy down to the black hole's edge. Gas must lose energy and angular momentum to fall in plain terms, it needs to slow down and spiral inward, and this process is messy and poorly understood. Think of leaves caught in a slow whirlpool on a pond. Sometimes they drift toward the drain, sometimes they circle forever. The exact mix of currents, sticky patches, and gusts of wind matters a lot. In Sagittarius A*, the winds are heating, magnetic forces, and collisions among gas clumps, and teasing apart which of those does the heavy lifting is still a work in progress. Another open question concerns the black hole's spin and magnetic environment. A spinning black hole could drag space itself around it, changing how matter orbits and maybe launching streams of fast particles, but measuring that spin is hard. Magnetic fields act like stretched rubber bands in the flow, and when they snap or rearrange they can produce the bright flares we observe. However, we need more precise maps of those fields to say for sure. Observations that track tiny hotspots orbiting close to the edge give clues, yet translating those clues into a clear picture of spin and field strength is like trying to deduce a piano's tuning by listening through a closed door. The neighborhood around the black hole raises further mysteries. Clusters of fast-moving stars and clouds of gas interact with each other and with the black hole, and it's unclear how those interactions influence star formation or clear out material. There may be unseen compact objects, small black holes or dense remnants, wandering nearby and stirring the pot, but detecting them is difficult. Using stars as tracers is practical. Their paths act like footprints in the snow that tell us where mass must be, but the pattern is complex and needs long, careful watching. Finally, there are questions tied to fundamental physics. The region close to the black hole is one of the best places to test how gravity works when it's extremely strong, and small discrepancies could hint at new physics. Current images and spectra give important tests, yet higher resolution and more sensitive observations across many wavelengths are required to pin things down. Telescopes working together across the world are improving the view, but patience is needed, like waiting for a slow cooker to finish a perfect stew, and each new observation refines what we know while often revealing fresh puzzles to solve. How Sagittarius A* changes our view of black holes. At the center of the Milky Way sits a compact object that has forced astronomers to rethink what black holes really do and how they behave. It contains mass roughly 4 million times that of the Sun and pulls nearby stars into fast, tight orbits, which is one of the clearest pieces of evidence that a very dense and invisible object occupies the galactic core. Observations of those orbiting stars, such as well-studied fast-moving ones close to the center, act like test particles in a lab and tell us the size and shape of the invisible mass without needing to see the hole itself. Think of it as tracking people jogging around a lamp post to learn how big and heavy the lamp post must be. Direct imaging and light measurements from this object have turned vague ideas into concrete details. A global array of radio telescopes work together to capture the bright ring and dark center, essentially a silhouette, created by hot gas falling toward the black hole. The dark center is the shadow, and the faint boundary around it marks the event horizon, which is the point of no return for anything that gets too close. Picture a spoon stirring a glowing soup. The spoon's outline is hard to see, but the way the broth swirls and lights up around it betrays the shape. Those images showed that black holes are not just theoretical holes but have a visible structure when the surrounding gas lights up. The behavior of matter and light near this object has given us real tests of how gravity works in extreme conditions. Light coming from near the center is stretched and dimmed by intense gravity, which we can measure and compare with predictions. Nearby stars and gas clouds don't follow simple Newtonian paths, they wobble and speed up in ways a strong gravity theory predicts, and these that match observations help confirm those ideas. A simple life comparison is driving uphill. A car needs more gas to climb, so it slows or the driver shifts gears. Light escaping a deep gravity well loses energy in a similar way and shows telltale signs when we measure its color and timing. Surprising behavior has changed expectations too. Instead of a constant, roaring engine, this black hole is often quiet and only flares occasionally, sometimes emitting bursts of 10th rays and infrared light. Those flares come from magnetic fields and hot gas interacting, roughly like rubber bands in space twisting and snapping and flinging particles, only much more energetic. Because this central object is relatively close by, these flickers happen on short timescales, giving astronomers a fast-paced laboratory to study how plasma and magnetic fields behave near extreme gravity. That helps explain activity from other, more distant black holes as well, because many processes scale up or down with mass, like how a backyard windstorm and a hurricane follow the same physics at different sizes. Finally, knowing how this nearby supermassive black hole behaves changes how we look at galaxies and their evolution. Its faintness showed that not all big black holes are luminous monsters, some eat slowly and quietly, and that affects how stars form in their neighborhood. Lessons learned here help astronomers interpret messy observations of faraway galactic centers where details are blurred. In short, this object has turned black holes from largely theoretical beasts into practical, observable objects with personalities, sometimes calm, sometimes noisy, and that shift makes the universe feel both less mysterious and more entertaining. So that's the story of Sagittarius A*, the giant, mostly quiet heart of our galaxy. Quick recap: at the center of the Milky Way sits a supermassive black hole weighing millions of suns. We know it's there because nearby stars race in tight orbits and radio telescopes have seen the bright ring and dark shadow that mark its edge. A black hole is simply a place where gravity is so strong that light can't escape. Think of a bathtub whirlpool or a merry-go-round that throws objects outward unless they keep their distance. It's not a cosmic vacuum cleaner that will suck up Earth. We're about 26,000 light-years away, safely orbiting along with the rest of the galaxy. If this journey made you look at the night sky a little differently, you and First are on the same page. We live inside the story we just told. If you enjoyed the trip, like, subscribe, and tell us in the comments what puzzled you most. Next time we'll explore how black holes grow and what would happen if you took a very bad elevator ride toward one, explained simply, with clear visuals and maybe one bad space joke. Thanks for watching, stay curious, and see you on the next orbit.